if the performance of a particular student is not good, he is getting a D grade, lowest grade or something like that, university will accept him. He said, okay, your performance is not that good, but you can still come and study here. But if the student is a criminal, involved in all criminal activities, what the university will say? He is a student, is a very good, A+ student, but he is a criminal. University will say, you get rusticated from the university, right? We don't require this thing. We may require some bad performance students, but not criminals. Suppose one student has got some psychological aberrations, some mental problems, right? Depending on that, he is a mad fellow. Similarly, a system performance may be little bit poor, we can tolerate it. It's not an issue at all. But under any circumstances, the system must be stable. System must be stable. So this is the case for the last so many years. So many years means maybe 100, 200 years. People are talking a control system must be stable. Recently, with the introduction of the internet and network control system and the safety critical systems, not only the system should be stable, but system should be safe. Safety property and stability property, they are not necessarily related. A system is stable, not necessarily it is safe. A system is stable, is not necessarily it is safe. I am giving an example. Suppose you are cliff of a mountain, cliff, okay? Now, you stand, you see, we went to that day on that beach, which beach, Koberam or something like that, Kaberam, okay? So that beach, I see there are many young people, the lovebirds, they are there, and they were standing just on the cliff and taking photographs. I've seen it, I saw it. Stable, but is it safe? It's not safe. But a point. So stability and safety do not often go together, may not go together, okay? So the two properties are extremely important. System must be stable, right? What is stable? We all know, so just for the sake of, if you have got an equilibrium point, if the system, if there is an equilibrium point xc, if you slightly perturb from the equilibrium point, it must, whether it is returning to xc, remain close to xc, or diverge from xc, right? Got a point? Say for example, here. These diagrams you all know, so I'm just doing it for the sake of completeness. This is asymptotically stable. This is unstable. This is Lyapunov stable or neutral stable. If you just give the perturbation, it will go nearby and stay there. It will not neither diverge, these things, right? How to study the stability of a linear system? Linear system has got only one equilibrium point, first thing, it has got one equilibrium point. And that is stable if all the eigenvalues are in the left half plane, right? In the left half plane eigenpoles, system is stable. Right half plane poles, system is unstable. Imaginary axis pole, marginally stable, actually unstable. Marginally stable is an academic thing. It is an academic job. No marginal stability. Nobody will put you on the cliff of a mountain and you are marginally stable there. No, no, no. That is practically unstable. So we say there is nothing like practically marginally stability does not exist. We cannot take that risk that we will ask the people to stand on the cliff because you are marginally stable. If something happens a little bit, you are gone, right? So marginal stable is an academic thing, I will tell you, but so system is stable or unstable, right? Left half of the S-plane, system is stable, right half of the S-plane, system is unstable. Now the question is how to study the stability of a nonlinear system, right? Nonlinear system analysis, even now people are doing like this. How they do it, I will tell you. They have got a nonlinear system, let us say X dot. They have got a nonlinear system, X dot is equal to Fx u, nonlinear system. They find the equilibrium point. First point is find the equilibrium points. Equilibrium point or points, depending on whether the system has got multiple equilibrium points. Then they found the Jacobian, they compute the Jacobian matrix. Del F over del X, I am not putting U here. At each equilibrium point, X is equal to X star. They found the Jacobian matrix, and then they compute the eigenvalues of this Jacobian matrix. Compute the eigenvalues of the Jacobian. See? Yes. Compute the eigenvalues of the Jacobian. Okay, compute the eigenvalues of the Jacobian. Then if the eigenvalues on the left half of the S-plane, system is stable. Right half of the S-plane, system is unstable, right? That is what people do it, analysis. You may laugh. The system is nonlinear, and people are using this linear analysis. Each equilibrium point, they found the Jacobian, they linearize the system, okay? Then develop the controller. Does it have any basis? Is there any justification to do like this? The answer is yes. What they are saying, they are not fool. Okay, they cannot be very genius, but they are not fools. It has all come from the Lyapunov's theory. Lyapunov has developed two methods. The first method says, what is the first method? I am telling the statement here. Compute the Jacobian matrix A of the system around the equilibrium point. Compute all eigenvalues of the matrix A. Then the equilibrium point Xa of the nonlinear system is asymptotically stable if all eigenvalues of A are negative. Right? Lyapunov's method. Unstable if any of the eigenvalues is positive. But if any of the eigenvalues lie on the j-omega axis, inconclusive, you cannot say that equilibrium point is stable or unstable. Clear? This is the Lyapunov method. So that gives the validity, okay, to analyze the system by using the Jacobian linearization. This is called the Jacobian linearization. Tomorrow we will study feedback linearization. Two things are different. Okay? Jacobian linearization, what it does? That is a system, it is nonlinear, okay? And you go and tell him that I know that you are idiot, but please don't move around. You just move in your own seat. Don't go further. That is how the system is allowed to operate within a small region, and then you do it. Jacobian linearization. Feedback linearization, which we will study tomorrow, if the system is nonlinear, you are a bloody idiot, get out. Go out of the class. Completely eliminated. No question of compromise. What my point? Jacobian linearization is a compromise. That the system is allowed to operate within a small region around the operating point. Okay. Feedback linearization, no. Remove it. System is nonlinear, remove it. Right? Okay. Lyapunov told that you have got a nonlinear system, you get the equilibrium point, find the Jacobian, compute the eigenvalues. If the eigenvalues are negative half, absolutely fine. If it is in the positive half, it is unstable. But if it is in the J omega axis, then my method will not work. You have to resort to some other method. Clear? And most of the cases in power system studies, the Jacobian matrix eigenvalues are negative. So therefore, that analysis is also valid. Okay? Asymptotically stable. Asymptotically stable, I will tell you, because you are all academics, so how you are going to teach to the students about asymptotic stability. Asymptotic means as the time tends to infinity, how the system will behave, right? This one, you perturb it, it will finally come to this point, right? Right? Say for example, if I draw like this, if you are here, and you go on, finally you will come again to this point, okay? When we were student, in class 8 I was studying, there is a poem, I did not find out actually now, that poem name is The Quest. I always give this example to explain the asymptotic stability, The Quest. This poem is being taught to us in class 8. I will tell you what is that. There is a mother and son. Father is not there. So they were living in a very nice house, okay, near the Miramara beach. In where? In Goa, Panji. Very nice place. They were staying together, the mother and son. Then one day the son told to his mother, Mom, I don't want to live here. I am getting bored. Very common term in nowadays the youngsters. We are bored. What is this bloody boredness? I don't understand. Anyhow, the mother told, why we are bored? It's a very nice beach. Huh? No, I want to go and find out a house, quest. Then mother finally told, okay, you go and find out a house, then we will shift there, right? Then the son went. You see, this is the house, this is the beach, house. The son, now he went in search of the house. Okay? Then he searched and searched and searched. After 1 year, he returned. Then his mother asked, did you find the house? He told, yes, I have found the house. What it is? It is here and here and here. Asymptotic stability. You see, goes from this point, move around, and finally come to the same point. Right? Got a point? This is a quest. This is a very nice song. It is being taught in, this is a clear example of the asymptotic stability. Right? So, if the eigenvalues on the left half of this plane, system is stable, asymptotically stable, right half unstable, these things. If it is not, then Lyapunov gave a different technique. What he did, I am giving the concept and then I will tell you the mathematical significance of that. Now you came to the lecture today with lots of compulsion because you have taken leave from your institute, okay, and it is all recorded here by this video here. Are you taking any video of those people? You take the video of those people, they should be in trouble. I should not be always trouble. Huh? So their principal will see whether they are attending here or they are going to see the beach of Goa. Okay, these people in the GAN people should listen to this. Okay, doesn't matter. You have come here. See, the concept is here, simple. You have come here. You have taken food in your hostel or in the hotel, right? As time progresses, you have already gathered some energy, right? By taking food. As time progresses, if your energy comes down, then you are stable. Because as the time progresses, if your energy goes, no, instead of coming down, it increases, then you are unstable. Just like your daughter, her daughter's energy I have seen 2 times. As the time comes down, then she becomes very angry. You see, unstable system. There is no energy, feeling hungry, but still shouting with the mother. No, I will not take this thing, I will not take this thing. You got a point? Unstable system. Clear example of unstable system. So, Lyapunov told, let us do one thing. I have got a system. Let us find out a function which is not exactly the energy of the system, but almost similar to the energy of the system, and analyze. As time progresses, that energy is decreasing or it is increasing. If it is decreasing, system is stable. If it is increasing, they have not told, no, I cannot say anything. That we'll see. If it is decreasing, system is stable. That's all. Full stop. Full stop there. If it is increasing, no, you cannot say system is unstable. Some other things are there. Okay? So let us find a function and differentiate that particular function and check whether that function is decreasing. If it is decreasing, system is stable. Right? This is the Lyapunov method. So Lyapunov function is an energy function. Lyapunov function, that function which will describe not the exact energy of the system, but energy-like function, right? So you find a Lyapunov function Vx, we say x is the state variable, a function, the energy function or the Lyapunov function. Find v dot x. V dot x is the differentiation with respect to time. That is dvx over dx into dx over dt. That is equal to dvx over dx into x dot. Find v dot x. Get the energy function and differentiate it. If it is negative, system is stable, asymptotically stable. System is asymptotically stable. If v dot x is less than 0, v dot x is less than 0, system is stable. V dot x is less than is equal to 0. If the is equal to 0 is there, the system is Lyapunov stable. That is, it is not asymptotically stable. Okay? So for that analogy I gave you, it is not coming to Miramar beach, it is going to nearby another beach. It is remaining close. It is not going out of this space. Okay? System is Lyapunov stable. Okay. So we take a function v Vx, differentiate the function and see whether it is negative. If it's negative, system is stable. Right? Clear? Okay. Let us do the function, energy function usually is a quadratic function or a even function. You remember one thing, Lyapunov function does not describe the energy of the system because you don't know the energy of the system. You take a function which can be used, which can be a possible candidate for the energy function. I will explain these things. This glass, a glass can be a possible candidate to store liquid. Got a point? I cannot take this iPad as a possible candidate to store liquid, right? So Lyapunov told, you take only that function. You are not restricted for that. You can take any function. You can take this glass or you can take another bowl. Okay? You can take a big bucket. That's fine. I have no problem. But don't take a plate. Because you describe the system, you take a function which is a possible candidate for energy. What is a possible candidate for energy? It is a quadratic function or an even function. X square, x to the power 4, x to the power 6, no excess q. No excess q, x to the power 5, right? They are not the possible candidate for energy functions, right? You take any functions of that order and then differentiate it and find out. We'll discuss these things. Let us take an example first and then we'll see. Then we'll come back. Then we'll come back. 1 minute. Let me take the example. See here. x1 dot is equal to x2, x2 dot is equal to minus 3x2 minus x1q. You may try with the Lyapunov function 1 by 4 x1 to the power 4 half x2 square. It's a possible candidate for the energy function. Then differentiate these things. It is there in the handout, I'm not taking time. Now you differentiate it, v dot x is equal to minus 3 x2 square. Is negative or positive? x2 square is all positive, minus 3 x2 square is negative. So the system is asymptotically stable, right? You take a function which is a possible, again repeating the point, take a Lyapunov function is a possible candidate to describe the energy system. Not necessarily you should know these things. Okay.
But it should be nonlinear.
Yeah?
It should be nonlinear.
Yeah, because the quadratic, x cannot be a possible candidate. It will be x square only, x square 4, so it has to be nonlinear. It's energy function, so it is energy function. Now, okay. There is a catch here. What is the catch? You take a Lyapunov function, you differentiate it, then you check the sign of that function, whether it is less than 0 or it is not, right? Now, what you check? You check v dot x is less than 0 or not, right? How to check it? Simple system, you can check it. It's an inequality. This is not an equality. V dot x should be checked for negative definiteness, negative 0, right? So you have to solve an inequality, okay? V dot x is less than 0. How many solutions are there? There are many solutions. Suppose I will say, find out the value of x which is less than 5. Find the value of x which is less than 5. How many solutions are there? Tell me. How many solutions? Infinite number of solutions, there are many. Right? Now, when there are many solutions, you have to find out the feasible solution. LMI feasibility, feasible solutions. I'll give the feasible solutions. When we are studying in year 2, we have got a mechanical engineering design. During that time, the electrical students also study little bit of mechanical. We have got a friend, I'm not taking his name, he's no more there. He passed away. He's a very good friend. But don't take it seriously, okay? So, the teacher gave a design to design the spring of the, what is that? Truck spring. Spring of the truck, and you have to design a spring. All the loads, all these tensile stress, all these nonsense things I don't know. Any mechanical people are here? Okay, then I'm sorry. Then otherwise I would have used any language here. So mechanical people, you know, they use all this tensile stress, this stress, this stress. Using this mechanical civil people, as such you are stressed. And in their own talk and teaching also, they teach you stress. Oh dear. How can they use that term to stress? I don't know. Tensile stress, this stress. Then there's the stress from your wife. Then the child stress, my daughter's stress. How many stress? Anyhow. So that's the stress. So that fellow, I remember Dr. Patnaik was sitting there and we all designed. Feasible solution I'm telling. And he got an answer. He told, because I was the topper. I was the gold medalist there, but that doesn't matter. So I'm now completely useless. So he told, hey, Swai, you see my design. I did it. I told him, means you have done the design. Okay, I've taken the name. Colonel means his name. You have done the good thing. Then one of my friends, he laughed. He told me, means you will get a slap. You know what happened? Truck spring design, he has got the answer. 3 kilometer length. 3 kilometer length spring design of a truck. He went and showed Dr. Patnaik. Dr. Patnaik got that particular notebook, threw it to his face. You bloody idiot. You don't know your spring design, you are making 3 kilometers. Is it feasible? The truck. See, feasible solution. You got a point? Feasible solution. When it's an inequality, when there are so many solutions, you must find out the feasible solution. It is not an easy task. So, V dot X is a matrix, and you will find a linear matrix inequality, that is LMI. How many people are working on LMI? LMI feasibility. Linear matrix inequality, there is a package in the MATLAB freely available, semi-definite programming, and there is one YALMIP package. It will solve the LMI problem, linear matrix inequality problem, and it will tell you, give you some solutions. Then up to you, you have to find out which one is the feasible solution, so that system is stable, right? So you get a function, differentiate it, right? And I will tell you, if you see the people working in the control theory, real control theory, I have got a couple of students who was working on mathematical control theory. One expression for V dot X, you know how much, it will take 3 pages. I have got a paper in International Journal of Physics Systems. My one student in German aerospace now working in Chatura. He derived one V dot X, 3 page. V dot X, this, then he put it in the LMI, then got a feasible solution. I told Chatura, for publication purpose, you are doing it. Whether people use it, he also laughed. We are doing nonsense things sometimes, but we have to do it. There's no other way out. You will surprise. You take a system, you define a function, you take the derivative, then you put it in that LMI form, then put it in the SDP, it will give you the solution. It is not easy, right? In 1990, in International Journal of Control, there is a special issue came celebrating 100 years of Lyapunov theory, Alexander Mikhail Lyapunov. This Lyapunov theory is being used until now. There is no other theory has been developed to study the stability of a nonlinear system. I'm telling you. Until now, no other theory has been done, Lyapunov stability being used. So what is that? Take a function, differentiate it, it appears to be simple. Okay. Problem. Lyapunov stability is a sufficient condition. It is not a necessary condition. Lyapunov stability, which is being extensively used in the stability analysis of the entire, by the entire engineering community, is a sufficient condition. It is not a necessary condition. What is that sufficient? If the Lyapunov study, you do it, and you found the system is stable, that's fine. But if you found that the system v dot x is not equal, less than 0, that does not mean that system is unstable. See this point, v dot x is less than 0, is stable, that's fine. Now suppose v dot x is not equal to 0, this does not mean system is unstable. That means if you can find out some other Vx which will say that the system is stable. Right? Now I'm giving an example here. 1 minute. Yeah. No. The first method, you can always use the first method. You linearize the system, you find the Jacobian, then you find the eigenvalues. If the eigenvalues in the left half of the S-plane, system is stable, there is no need of finding the Vx. If the eigenvalues are on the j omega axis, then you have to resort to this particular formula. Good question. Now, I will not start with the first method. Those people who are not control specialists, they should start with the first method, because linearize the system and do it. Okay? Linearize the system and do it. Linearization of a system, which we will talk tomorrow, the feasibility, linearization, Jacobian linearization, this is just like our Indian government is working. Appeasement. Not only Indian government, throughout the world, appeasement politics. A person is idiot, and you tell him, you are idiot, or I am not throwing you out, you better behave a little bit, be within your certain range, you stay here. Okay? But feedback linearization, other type of techniques are, if it is a linear or non-linear, remove it, completely remove it from the system. So Jacobian linearization is okay, no doubt about that. Now see here, I'm saying this example here. This example, is it? Now this example, I'm just showing the result. 1 minute. This one is plus minus J1, not J omega, that's typo. Now here, this particular system, I found the usual first method. I got the Jacobian, I got the eigenvalues of the system, and the system eigenvalues are plus minus J1. So now I cannot use the first method. So we use the other method, and then we found out, okay. Actually, this particular line is also wrong. I just show it for the students, I do it, I should remove it. A minus B, x1 square, x2 square. So if A is less than B, system is stable. If A is greater than B, that I have written it for the student's sake. Actually, I should not write it. Nothing can be done. If A is less than B, system is stable. That's all, full stop. Lyapunov has got the stability criteria. Lyapunov did not give any instability criteria. Remember, Lyapunov stability criteria. Lyapunov did not give any instability criteria. Under what condition, if V dot x will be greater than 0, system will be unstable? No, that criteria is not there. Okay, this line I wrote it because for the students who say that V dot x is greater than 0, avoid it, but this is not true. The first one, Lyapunov said you get a Lyapunov function and differentiate. If negative, system is stable, full stop. If your system is positive, nothing can be concluded. Now I'm giving the interesting point here. This system, I took a Lyapunov function, you see here, I took a Lyapunov function, this one, and took the derivative. Now this one, this is inconclusive, yet minus x1 qx2. So whether it is negative or positive, you don't know. Whether positive or negative, you do not know. So Lyapunov, using this function, it is inconclusive. System is same. I change the Lyapunov function. Then it is conclusive now. Same system. Right? So Lyapunov function, if it is negative, system is stable. If it is not negative, you keep mum. Nothing can be told. Right? Nothing can be told about the stability of the system. That is the problem with the Lyapunov function theorem. There is no method how to find out the suitable Lyapunov function. Although people give some methods, but having said that, although theoretically we say that we cannot find the Lyapunov functions, but now most cases, around 99.9% cases we found out. Usually the Lyapunov function is X transpose Px. E transpose P, usually we find out. All the cases we have been doing it. Which one? No. Here is the equilibrium point. Here is telling for the all things, all cases. But in other cases for each of the equilibrium points. I'm giving an example here. Suppose I have got a nonlinear system. I'm giving the let us ask me like this. Now this system has got one equilibrium point here, another equilibrium point here, another equilibrium point here. 3 equilibrium points. This is a stability boundary, stability surface. Now this is equilibrium point 1, E1, this is E2, and this is E3, right? I have got the system x dot is equal to Fx, right? Now I found the Jacobian matrix Ga is equal to del F over del x, right? Now very clear Jacobian function matrix del F over del x at E1 will have got eigenvalues where? Right up or left up? Huh? Right up, because this point is unstable. You see, this equilibrium point is unstable, yes or no? This equilibrium point is unstable. So if this equilibrium point is unstable, it is obvious. So the Jacobian matrix here will have eigenvalues in the right half of this plane. This or the other equilibrium point here, where it went, I don't know. this equilibrium point, this equilibrium point, this equilibrium point. E1, E2, E3. E2, if you find Jacobian matrix, E2 is stable or unstable? Stable. So this Jacobian matrix, so eigenvalue will be in the left half. And whereas E3, eigenvalues will be in the right half. Right? So this is how people analyze it. And this justifies, this particular theorem justifies the linearization analysis of nonlinear systems. Okay. If someone asks you that why you are analyzing, linearizing the system, you always cite the Lyapunov first method here. Because that justifies that this point. Anyway, any questions on this? The problem is there is no method how to find out the Lyapunov functions, but having said that, I'll tell you, usually we find out. Okay. There are many things have been developed nowadays. Lyapunov functions, because last so many years people are working on that. Linear matrix inequality, semi-definite programming, bilinear matrix inequality, sum of squares methods. These things have been developed in recent years to study the stability of the system, basically, essentially, using the Lyapunov method, right? You see, the problem is, I'll tell you, important thing you should understand, you can find out a Lyapunov function which can ensure the system is stable, but that is not a solution. You have to find out the boundary where it is entering into instability. Conservative result, non-conservative result. What is the meaning of that? I will tell you. A ship, this is the point. A ship is safe in the harbor. No problem. A ship is safe in the harbor. But that doesn't mean the ship should not sail, because that is the purpose which it has been built. Right? So you study the Lyapunov stability, you say, if the ship is within this harbor, it is stable. That's fine. But what's the point? You find out, you just take the ship little away from the port and see whether it is stable or not. Still further, whether it is stable or not. Still further, you see, this is the point I'm saying. This is the space. Lyapunov stability is stable. Is it stable here? Is it stable here? Is it stable here? Is it stable here? Okay, don't make it conservative. Okay, if you are inside the house, no problem of any accident. But that is not the purpose for which you are built, right? So that is a conservative. So while doing research, people will say, using this Lyapunov function, I found that if the system operates within this region, it is stable. Using another Lyapunov function, I found the system is stable here. So naturally, this one is better. Conservativeness, you know, is not conservative, a little bit expanding. No, that you have to do by trial and error, you see. Just increase it, just increase it. Yeah, the region will change. Region will change. No, the question is, I'll tell you like this. Questions are very good. It has got beautiful answers here also. All these problems lie with the Lyapunov condition, the sufficient condition, right? Now, you have got a weapon. You have got a weapon, right? How many people you can kill? It all depends on many factors. First thing, how many people are there? How long the weapon is there? Okay? So depending if you change the weapon, then you can do many other things, right? So similar thing, different Lyapunov functions will give you different results. Different Lyapunov function will give you different results. So nothing is conclusive. So in the research, what we do, we found out that this particular fellow is using this Lyapunov function and is showing the system is stable if it is remaining within this region. Then we define another Lyapunov function and we show that system is stable beyond that. Then, it is better. And then somebody, another third person will come, he will say, no, another Lyapunov function, they will show conservativeness. The conclusion, conservativeness. My controller, my Lyapunov function is less conservative. So that's the point. No, that thing in the first method. Yeah. It will talk about the entire system, nonlinear system. It has nothing to do with the equilibrium points now. No, we don't say about that. We don't say about that. Second method, we are straight away doing it. We whole system. Very difficult. Now, say for example, minus 3x2 square. B dot x is minus 3x2 square. So that x2, where it is doesn't matter. Be x2 square, it will always be negative. That's the point. So the question is, if, okay, I'll tell you. If the system is completely stable, if the system is complete, that the theorem says, if the system is actually stable, fully stable, no matter where the equilibrium points are there, then there exists a suitable Lyapunov function somewhere in the universe. That is the theorem. If the system is stable, there exists a Lyapunov function. No. You take a Lyapunov function and you find the stability. That's fine. Now suppose your Lyapunov function did not find the stability condition. So you don't say the system is unstable. You say that I cannot find out a suitable Lyapunov function. You can find out, you can search for some new Lyapunov function which may prove the system is stable. Because remember, Lyapunov is not in instability condition. There is no instability condition. Yes. They are not saying that. They say that if the system is stable, there exists a Lyapunov function. How to find out if that you have to search? So therefore, he is not giving any instability condition. But one thing is sure, if you prove it is stable, then it is stable. If you prove it is stable, it's stable. We'll give a break for tea, then we'll study about sliding mode controller. Any questions on Lyapunov stability? Are you getting something on Lyapunov stability or this is forcibly put on you? Little, some ideas? Some ideas there, that's fine. At least you say that you get something, so I will be happy. Even if you say that I am talking nonsense.